In this video, I'm going to show you how to properly design a PCB with an antenna on it. This is one of the most critical parts of any PCB design if the product has any wireless functionality. And it's something that I see done wrong a lot of the time, so I wanted to create a video to show you how to do it correctly. So what we're going to look at is here, I'm going to start with the schematic. This is a Bluetooth low energy transceiver chip. This is the feed line. You can see I've got it labeled just RF that goes through this Pi network or the CLC network. And then that goes to the actual Bluetooth antenna. So this is the feed line here. The reason for this LCL circuit here, or CLC circuit, is to allow you to fine tune the impedance matching. The goal is to have the impedance at 50 ohms impedance, and then that will give you the maximum power transfer between the antenna and the transceiver. I'm going to show you how to get that set as accurately as possible, but you still want to, in most cases, have a tuning circuit on there so that after you get the design finalized, you can send it off to usually a third-party service who will analyze the board and give you the values for this CLC circuit that will give you the maximum, the best impedance matching and the maximum power transfer. So this is the line that we're looking at here, and this is, you'll hear this called a feed line, an antenna feed line. A transmission line is a more general term. You also hear microstrip, which is a type of transmission line that we'll look at, and then also not as commonly, you won't hear this term as much, but it's the type of transmission line I prefer is called a coplanar waveguide. Here is the PCB layout. This is the Bluetooth transceiver chip. This here is the RF pin that I'm showing that then goes through the feed line, goes through this inductor L4. Here is the C2, the one capacitor for the CLC network. It just goes from the feed line to ground. This is all ground here, this copper port. So it goes through the inductor, comes out the other side. Here's the other capacitor for the CLC network. And then the feed line goes up to this antenna. And on this board, I'm using what's called just a chip antenna. It pretty much looks almost like a ceramic capacitor. Another option for PCB is what's called a PCB trace antenna. And that's where you don't actually add an extra component because this antenna actually has some cost to it. It's not usually too expensive, but the other option is you can actually design an antenna on the PCB. So if you see a PCB that's got like this trace that's out by itself, that's snaking back and forth, then that's a PCB antenna. The other option is you could put a connector here then for connecting up an external antenna. And all those cases, whether it's a chip antenna, PCB antenna, or an external antenna, you need the same impedance matching and the same design for this feed line. So this is what we're going to be focusing on, is this feed line and how to design it and how to get it to a 50 ohm impedance. And I just want to start off by clarifying that this is not 50 ohms of resistance. There's no resistor in this line. The impedance is the 50 ohm impedance, which is complex impedance, and that is actually between the feed line and the ground plane that's underneath of it. The software that we're going to use to calculate and fine tune this feed line so we can get the ideal matching is a piece of software that I like to use. It's called AppCAD, and it's available for free. It's an app that is owned by Broadcom. So just go to broadcom.com/appcad, and then you can just download it for free. Okay, I'm going to start up AppCAD now. And they have several different options here. We're going to do the transmission lines. I've never really used any of the other features of AppCAD. I mainly just use this purely for doing transmission lines. Okay, so they give you several different options. They have a microstrip. So a microstrip just has the feed line above the dielectric and then the ground plane on the bottom below the actual microstrip. Whereas a coplanar waveguide, which is very similar. So this is the feed line, and the only difference is there's also a ground plane on the top layer with the feed line. That's what you can see. Let me go back to my printed circuit board layout. So you can see this is all ground that's all around. Not only is there a ground plane underneath, I've got the ground plane here that's underneath of the actual feed line. Then also on the layer that has the feed line, I've got a ground plane that surrounds the feed line. And for that scenario, then you want to use the coplanar waveguide. We have several different specifications that we're going to have to enter here. Your goal is you want to get these specifications so you get this ZO equals 50 ohms. So you want this to be 50 ohm impedance. So let's just see, I've got everything just at the default. Okay, so we're at 115.7 ohms. So we have quite a ways to go. First of all, we're going to set what is called the dielectric permittivity. This is, they have here, what I would suggest is that you reach out to your PCB manufacturer and you can get this for their particular dielectric material. But there are various dielectric materials that you can use, and I'll go into that. But the most common one is FR4, and it's showing that it's got a permittivity of 4.6. Okay, now that we've got that set, I didn't have the right permittivity in there. Let's recalculate. Okay, that made a good difference. That brought it down to 69. Then next is this H. So what it's looking for is the height or the depth between the actual feed line here on this top layer and the ground plane underneath. If the ground, let's say for instance, you have a 4-layer board. If this is layer 1 and your ground plane is layer 2, then that's fairly easy. The height is basically going to just be the thickness of that dielectric material between layer 1 and 2. But you could have, on a 4-layer board, you could put this on layer 1 and the ground plane is on layer 4 on the very bottom. This is only showing the 2 copper layers, but in that case, you would have 4 copper layers. And what you would do in that case is you have to total up the height from layer 1 all the way down to layer 4. Basically, you're just calculating the height of the board, the thickness of the board between the feed line and the ground plane underneath. And I've got the length unit in mils, and that's pretty standard for PCB design. That's my preferred unit, which is just 1,000th of an inch. We can set the frequency here, which isn't going to be really important for what we're doing, but I'm going to just set it to 2.4 gigahertz. Okay, we've still, see the frequency doesn't obviously change the impedance, so that's not going to have any impact on that. Next, we have the width of the feed line itself, and then we have the space here, the gap between the edge of the feed line and the edge of this ground plane. I'm going to tweak this a little bit. Let's say if we take this up to 15, let's see what that does. Oh, that brought us down to 60 ohms. And then let's say I increase this gap. Let's see which way that goes. Oh, that went the wrong way. So I'm going to change that back to 5. And what we could do is, I don't think this is, let's see what this, the 25 is what it just defaulted to. Okay, you can see that's actually increasing the impedance. You can play around with these different parameters and see what it takes to get an actual feed line that matches the 50 ohm impedance that you require. So what we can do is, let's just say we take this up to 20. That's getting us closer. Let's say if we take this down to, we don't want to go below 5 mils. And what you can do is, let's say if you have a 4-layer board, because you can see as this number goes higher, impedance goes higher. What you may find out is if you put your feed line on layer 1 and your ground plane on layer 4, that this height is going to be so high that you have to have a really wide feed line to compensate and get the impedance down. So in that case, you could put your feed line on layer 1 and the ground plane on layer 2, and then you could just use that height between layer 1 and layer 2. Let's just say if you take this down to 20, and let's take this up maybe 25, which is still quite a wide feed line. But you can see now we've dropped down below 47.8, so we're below the 50. What I'm going to do now is I'm going to look at my printed circuit board here, and I'm going to show you what we can look at. My width of my feed line, if I can get it to come up here again, it's showing this width here 17.72. So I'm going to go back to here, and I'm going to put in 17.72. Now I'm going to go back here and I'm going to measure right about there. We are looking at about 8.5 mils. It shows it down in the bottom left corner. The length is 8.5 mils. So that's the space that I've got set there for now. Okay, I'm going to go here to 8.5. And we're still on the high side. Take this down to 10. There we go. So that brought it down. Yeah. The goal is to adjust these values, all of these, so you can get to 50 ohm. And you have a lot of knobs you can turn. You can change the height, which means which layers you put the feed line on in relationship to the ground plane that's underneath of it. You can also tweak the width of the feed line itself. You can tweak the spacing between the feed line and the ground plane. And those are the main parts that you'll tweak. The thickness of the copper has very little effect. You can see that just only changed it by 1/10 of an ohm. The other thing I want to talk about briefly is the dielectric materials. FR4 is the most common. It's like the default dielectric material, and that's what I'm using here. However, it doesn't have real tight control over this dielectric, the permittivity. So it can vary from lot to lot. And what happens is if your permittivity varies a lot, then that's going to vary your impedance matching. So you may get some units that are better matched than other units, and it's all just due to the permittivity variation from one board to the next. So in that case, what I would recommend is that you talk to your PCB manufacturer and ask them which dielectric material is best for an RF application. And in those cases, dielectric materials that are good for RF applications have tightly controlled permittivities, so that will give you much tighter control over the impedance matching. I do want to briefly show a couple things here I forgot to mention. First of all, you can see that this opening here, there's no ground anywhere on any layer in this particular what's called a ground clearance zone. And you need to look this up for your specific antenna if you're using a chip antenna. It will be different if you're custom designing your own PCB antenna, and that's a lot more complex. So I would suggest in most cases, you're going to start off with a chip antenna. You need to look up what this ground clearance zone is. So you can't have any ground metal above or below the chip antenna. That's why you see this opening here. Secondly, you'll see all these vias here, and this is just called stitching. And these basically just stitch this ground to the ground plane that's underneath of it. And you just want to make sure you have this as a really solid ground. And that's why you'll see all these vias, basically as many as I could get in around this feed line and the antenna itself. That's really important to do as well, as to include that. I would say that in most cases, I suggest that you start off with using a module. And so instead of designing what I just described, you would instead buy a module that has this chip, has the antenna and feed line, everything on it. So they've done all this for you. And then you just basically solder that board, that module onto your printed circuit board. The main advantage to that, not that this is really too complicated to do now that I've shown you how to do it, but the main advantage is if you buy a board that's already got the antenna on it, then it's most likely already FCC certified. So it just simplifies the certification process. Whereas when you design it from scratch like this, it's going to have to be classified as an intentional radiator, which is a more stringent requirement for FCC certification that's going to be more expensive and more complicated. Okay, I hope this has been helpful. I'm John Teal with Predictable Designs, and I hope you have a great day. Hey there, this is John Teal, founder of Predictable Designs. If you enjoyed this video and you want to keep learning more about developing, manufacturing, and selling new hardware products, then be sure to subscribe to our YouTube channel and also check out the websites predictabledesigns.com and thehardwareacademy.com.